Okay. My name is Igor Kuskovsky. I'm working at Queen's College of CUNY, but I'll present kind of results that obtained at Queen's College, at University of Buffalo, and with the theoretical work support from Ohio University and University of Antwerp. And I call it experimental observation of optical Aharonov-Bohm effect in stacked type 2 quantum dots. So the reason is because there were a lot of work done theoretical on prediction of Aharonov-Bohm oscillations in quantum rings or type 2 quantum dots. However, very few experimental observation available until now, and our system is one of the few. So I'm going to show you experiments. First, because it's a very diverse crowd, I'll quickly tell you what I mean on the type 2 quantum dots. So basically, it's a so-called type 2 band alignment, give you general expectation for photoluminescence behavior. Then I quickly introduce our specific system, which is a zinc-telluride select quantum dots. Then I will tell you what we understand as the optical Aharonov-Bohm effect, because terminology could be different. And then I show you the experimental results. So type 2 band alignment, if you have two heterostructures, let's say quantum dots, in the semiconductor, you can have basically two types of band alignment. One, when the material of quantum dot with a smaller band gap is completely within the band gap of the material with a larger band gap, we call it type 1. That means the electron and hole will be confined with the quantum dot, so spatially they will be sitting in one region. But then you can have a situation when, let's say, conduction band of a quantum dot material is below conduction band of the barrier material, but the valence band is below of the valence band of the barrier material, and the same for electrons. Then that means if you create electron-hole pair, in this case, electron will be confined to the quantum dot material, but hole will be within the barrier. And in this case, hole will be within quantum dot, but electron will be within the barrier. That means the electron and hole are spatially separated, forming a dipole, which obviously is the crux of the problem. So interestingly, that if you look at perfectly ideal type 2 quantum dot, in this case, since our system is of this type band alignment, as I'll show you later, you can do the calculations, and you can show that if that's a z direction, growth direction of ideal single quantum dot, electron would sit on the top and the bottom of the quantum dot. So if you apply magnetic field along the growth direction, you'll not be able to see Aharonov-Bohm effect, because you need cylindrical geometry. So in this case, the stacked quantum dots would be very useful. So what is the general optical behavior type 2 quantum dots? Again, for those who didn't work with that, you can show, and I'm not going to go in details, that if you have emission from type 2 band alignment, as I show here, weak excitation and strong excitation, you have a change of the band structure in such a way that emission, CW emission, actually shifts to the higher energies with excitation intensity, and usually it follows at the cubic root of excitation intensity. Then it has certain behavior in a lifetime that it's relatively long, because again the overlap wave function between electron and hole are small because they're spatially separated. I'd like to point out that this indirect in the real space, they still direct exciton in a K space, so you don't need to have any phonon-assistant recombination for photoluminescence to be observed. And again, time decay changes with excitation. When you pump hard, it's relatively fast. When you pump weaker, it gets slower, and at very weak pumping, it's very, very slow. And because this change is due to the concentration of photogenerated carriers, these three curves have to lie on one master curve, and this is theoretical calculation, the solid curve, and they all lie on the master curve. So that's a basic idea of the type 2 band alignment, be it for quantum dots or quantum wells or quantum wires. So our specific system is the following. It's a multi-layer system of the stacked quantum dots. They're grown in a specific way. Again, for those who know self-assembled quantum dots. Most of the time they're grown by so-called Stronsky-Krasnov method. It's when you grow a thin strain layer which cracks to relax the energy. Instead of forming dislocation, it cracks and forms the quantum dots. Basically, quantum dots, it's a cracked film or strain film of the overgrown lattice mismatch layer, which is usual case of indium arsenide, gallium arsenide, or cadmium selenide, zinc selenide structures. Ours are not grown the same way. They're grown in a little bit more complicated way. So we first grow the barriers, and then we use so-called migration-enhanced epitaxy when each element, zinc and tellurium, are deposited sequentially with the time for tellurium to be finding its minimum energy position. And kind of schematically, we show it here. You have each layer, which I will call quantum dot containing layer, which it's grown by this repetition. And these periods are repeated many, many times, about 200 times. So the dots get stuck. So that's a high-resolution X-ray, so you can see superlattice periodicity, which is in the period of these stacked dots. And this is electron microscopy image, so if you want to believe, these are our stacked quantum dots. So that's an optical emission, and what we will be concerned is only with this luminescence band, which is green. That's the band relates to quantum dot emission. And that's a general band alignment for zinc telluride quantum dot, zinc telluride, zinc selenide quantum dot at low temperatures. You can see that hole is strongly confined in a very large 1 electron volt potential. And electron is in the barrier, and it has very high energy potential to penetrate into the dot. So it forms a perfect, very good cylindrical symmetry. So, what we understand in the optical Aharonov-Bohm effect is basically is a manifestation of Aharonov-Bohm phase in optical emission of especially indirect exciton in type 2 quantum dots or quantum rings. What's important that overall charge of this quadriparticle is 0. However, you have an electric dipole which interacts with the vector potential, and you're supposed to have Aharonov-Bohm oscillations. The difference is that it oscillates with the periodicity of the flux between electron in the hole orbit. And depending on strength of electron-hole coupling, you can have theoretically, ideally, two cases. Case number one, when electron and hole move independently. Basically, it's a single particle approximation. So you can write the excitonic energy in this form for electron and for electron orbital momentum and hole orbital momentum independent. What is interesting in this case that the ground state will change sequentially from 0 plus 1, minus 1 plus 1, minus 1 plus 2, and so on. That means total orbital momentum of electron-hole pair will be changing from 0, 1, 0, 1, 0, 1, and so on. Why is that important? Because usually when we look at the energy oscillation and Aharonov-Bohm oscillation, it's kind of self-evident. But however, in a semiconductor, in an optical transition, there is another effect appears, which is not so obvious for those who don't do this. Because if you change the total orbital momentum from 0 to 1, you have a selection rule forbid your optical emission. So in addition to oscillation in energy, you expect oscillation in intensity of your photoluminescence. So to show that you really have this effect, you have to have two things. You have to have energy oscillation in excitonic emission, but secondly, you have to have oscillation in intensity. So you have to have bright and dark exciton, bright and dark exciton. And of course, the second case, when Coulomb interaction is important, then you have to consider the exciton as a total, and then you have to work with the total orbital momentum. And here is a little bit less interesting in a sense, because you expect only one oscillation. But of course, in real life, it doesn't happen. We have more oscillations because of the you have defects, and you have not perfect symmetry, and you have a coupling of different orbital momentum and relaxation of selection rule. So that's introduction and theory. Let's see if we could see it experimentally. And before I show you the data, I quickly will go why single dot versus stack dot, because, and again, the single dot I already show. However, if you have a stack dot, you can do again in a single particle approximation. You can do calculation and can show that actually electron field electron wave function would not sit on the top of the quantum dots. It would be shifted to the side. So if you apply magnetic field along Roche direction, you will have perfect cylindrical symmetry to see the electron motion. So that's details of the model. Because of time, I will skip it. And I'll show you the data. So that's measurements of photoluminescence, which relate to quantum dots in the magnetic field at the different excitation intensities. So it's interesting that at high excitation intensity, we see very small wiggle here. However, it pertains to specific properties of our system because it has strong isoelectronic bound emission, which you have to suppress to see emission from quantum dots, which we've done by reducing excitation intensity, and we see these nice oscillations. It's important to point out that it's a quantum dots, not a quantum wells, because in quantum wells you don't have the closed orbit, so you'll not see the oscillations. And people, of course, obviously have done on magneto-optical measurements on quantum dots. They saw the overall decrease in intensity, but not the oscillations. So I'll show you here in a little bit more details in one of the samples, so you can see very nice oscillation. And this happens at phi 0/2. And because system is not symmetrical, you can show that it has to be another feature appear at exactly twice the magnetic field, and we do see it. This is we're done for 3 samples with the different size of quantum dots to show that it's really not a one sample system. But what is interesting, I'd like to point out that as a tool, this Aharonov-Bohm oscillations as a tool is very, very important, because the magnetic field transition goes as inverse as the radius square, and magnetic field is the first power. So basically, if you take 1.79 Tesla versus 1.76 Tesla, it's very easy to resolve. That means if you recalculate, for instance, the orbit of electron with the 19.5 angstroms and 20.5 angstroms, it's very well resolved. So you cannot say this is approximately 20 angstrom. They're different. And this tool is very important, and we really saw that effect. So that's intensity oscillation. So now we had to do a little bit different experiment with the focused laser beam, and it was done at the same samples at University of Buffalo. So that's we had to do a little bit more precise measurements and do fitting of the curve. And if you do that, you really can resolve very nice energy oscillation of the exciton. And at the same time, you can see oscillation in emission intensity. If you calculate radius of the orbit from this oscillation, we get about 23 nanometer. And from the stacked model, I kind of mentioned, we estimated about 17 nanometer for the radius of the electron. So that allows you to measure the quantum dot radius. So why is that such a strong effect here? And I have to go a little bit back to the stacked model. If you have a self-assembled quantum dots, the problem is that they're all different sizes. So if you look at a single dot emission, you don't expect to see very strong oscillations, because each quantum dot will have oscillation in different magnetic field due to different radius. However, if you have a stacked model, what happens, the electron moves along the whole column, and basically averages out the not only size of the quantum dot, but mis-stacking of the quantum dot. Because if I have a quantum dots like this, the electron will move in the whole orbit, and that's why the effect is so strong. So the having stacked columnar structure is very important for observation of this type of effects. And I think I'm out of time. So I have to, I'll just quickly go and say that we saw, there's nothing new in the sense of measurements, but we did measurements up to 180 Kelvin. And I think is the highest temperature at which Aharonov-Bohm oscillations have been observed. So a summary, and finally, I'd like to thank a group of Professor Maria Tamarga at City University who actually grew the samples. Thank you.
To which theoretical limit your experiment is closer? You mentioned limit of no-Coulomb interaction, independent electron and Hopf, and opposite limit
Okay.
exciton. Is the experiment more close?
Both. And the reason being we cannot distinguish, because if you saw the calculations, and in this case, Hall is basically very strongly confined within the quantum dot. So for all practical purposes, Hall doesn't move, and what's happening is only due to the electron motion. So so assume that Hall is basically radius of the whole orbit is 0. So you have to assume that the whole orbital momentum is always 0. Then you have to be close to the single particle condition, because only electron changes its orbital momentum. In a quantum ring, you can achieve both, because the Hall will have to move. In the quantum dots, it's a trickier situation, because usually the carrier which is confined to the quantum dot is the wave function is in the center.
I wonder whether you see any correlation of the width of the Gaussians that you fit to get the energies in intensities. Do they also oscillate with the flux?
The width of the Gaussian peaks, I didn't check into that. We just fit that and get the peak position. But width, it's a complicated system because we have isoelectronic bound excitons there. And again, to get you the full flavor of this, I have to go in the specific of the system. And I can tell you that quantum dots probably here, but this could be isoelectronic bound excitons. We really can't pinpoint exact transition from isoelectronic bound excitons to the quantum dots. And they do oscillate too. And as I said, I have out of the time, we saw the oscillation of the peaks, which has nothing to do with the quantum dots. We don't understand it. Yeah, I can, again, I kind of have it at the end. So I can quickly show you that we see the oscillation like this on the peaks, which have nothing to do. This, if you do the basic analysis of the photoluminescence, you would assume there is no quantum dots there. But if you do magneto-optical measurements, you see Aharonov-Bohm oscillations. And that's another one of the puzzles we don't understand yet. So that's the only thing I can answer you. Thank you.